right now, your voice is being chopped up into thousands of tiny separate digital blocks, thrown into this chaotic global traffic jam, and then reassembled on the other side of the world in literal milliseconds.
Yeah, and it happens without you even noticing.
Exactly. And welcome to the deep dive. You probably already know the internet isn't some magical, invisible cloud.
I was right, definitely not.
It's a massive, highly structured physical grid. We're talking copper, glass, code. And today our mission is to take you from an absolute beginner to an absolute master of the architectural mechanics in Lecture 01 on data communication networks.
It is a fascinating set of notes, and I'll be acting as your personal academic mentor today.
Which we definitely need.
Yeah, because when you strip away the dense academic jargon,
Yeah.
what you're really looking at is the blueprint for modern human connectivity. But to guarantee you actually succeed and understand this, we are going to use a strict, foolproof four-step framework for every single question we cover today.
Oh, I love a good framework. Walk us through it.
Okay, so step one, we read the exact question. Step two, we trace it back to the specific source slide so you know where it came from. Step three, we break down the exam strategy to actually solve it.
Right.
And step four, we deliver a, PhD level conceptual deep dive using real world analogies. So it actually sticks in your brain.
That is perfect. By the end of this session, you are going to understand exactly how this invisible digital web around you functions. I mean, from the basic rules of communication to the literal physical math of data traffic.
Let's jump in.
Okay, let's do it. Step one, let's state the question. I'm going to read it right now. Question one, what is meant by the following terms? A host, B protocol, CISP, DIXPE, peering link.
Okay, step two, source tracing. You're going to find this in the early slides titled Components of Data Communication Systems and Internet Structure, a network of networks.
Got it. So what is step three, the exam strategy here? Because reading through the notes, it feels like there's a trap. It's so easy to just memorize, like a laptop is a host.
Yes, that is exactly the trap. If you just memorize examples for the exam, it's a dead end. The strategy here is to provide the functional definition.
Right.
You need to explain what the component actually does in the network, not just name a device.
Okay, so step four, let's do the PhD level deep dive with analogies. Let's start with host and protocol.
Well, a host is an end device, sure, but its functional role is to be the origin or the destination of data. But hosts need a protocol.
Right, because without a protocol, those hosts are effectively useless. The analogy from the text that I really like is language. A protocol is just a set of rules.
Exactly.
Like, you could have two hosts, say a phone and a PC, connected by the fastest fiber optic cable on Earth. But if there's no protocol, it's exactly like a person who only speaks French trying to talk to someone who only speaks Japanese.
The physical connection is perfect, but there is zero comprehension.
Yeah, the protocol is the shared translator.
That's a great way to put it. Now, building on that for the rest of the terms, ISPs, and peering, if we imagine those individual hosts as houses, an ISP, an internet service provider, well, that's the system of roads connecting the houses.
Okay, I'm picturing it.
So your local ISP provides the neighborhood streets, but to get your data to another continent, those streets have to merge onto global superhighways. And those are the Tier 1 ISPs.
Wait, hold on. This is where I get stuck on the economics. If Tier 1 ISPs are these massive competing toll road companies, why would they ever let traffic cross from their toll road to a rival's toll road?
I mean, wouldn't they just charge massive fees?
Yeah, that seems like the default capitalist move.
It's a really good point, and it brings us right to IXPs and peering links. An ISP, an Internet Exchange Point, is a massive physical intersection where these competing toll roads meet. And the peering link is a specific agreement between two networks to let traffic cross that intersection without charging each other a toll.
Wait, really? They just dropped the tolls entirely?
They do, because it mutually benefits both of their customer bases. If they charged a toll every time an email crossed networks, the internet would just fragment into isolated walled gardens.
Oh, wow.
Yeah, so the peering link is the handshake that creates a true network of networks.
That makes a lot of sense. Okay, so moving on. Now that we have our houses and roads defined, we need to know how to map them out based on the size of the territory. So, step one, question two. I'll read it. Identify the most suitable network topologies. Bus, ring, star, tree, mesh for different network extents. PAN, LAN, campus network, MAN, and WAN.
Step two, source tracing. This maps directly to the network extent and network topology slides in your notes.
Okay, step 3, exam strategy. How do we tackle this?
The trick for the exam is to pair the physical scale of the network with the complexity and cost of the topology.
Right.
Small scale equals simpler, centralized shapes. Massive scale demands complex, highly redundant, and much more expensive shapes.
Okay, so step 4, deep dive and analogies. Let's use city planning, starting with the absolute smallest, a PAN or personal area network.
Right.
This is basically just your desk. For a PAN, a star topology works perfectly. Your laptop is the central hub, and your mouse and keyboard are the spokes. It's cheap, efficient, perfect for a tiny space.
Precisely. And as we scale up to a LAN, a local area network, maybe a single office building, we still lean on that star topology, usually with a switch in a closet.
Yeah.
But look at the WAN, the wide area network. We're talking networks spanning thousands of kilometers. This requires a mesh.
Wait, why? Because it's like a global airline route map.
Exactly.
If one major hub goes down, say a cable gets cut in the ocean, you have to have redundant links to reroute that massive volume of traffic. But I'll push back a bit. Why not use a mesh for everything?
Like a mesh for your office LAN.
Yeah, why not have ultimate reliability everywhere?
Because the physical reality of a full mesh is an engineering nightmare. Every single device needs a dedicated wire to every other device. For just 100 computers, that's nearly 5,000 physical cables.
Oh, wow. Okay, yeah, that is astronomically expensive and probably impossible to fit in the walls.
No. Exactly. So mesh is strictly for massive, critical infrastructure.
Which sets up our next segment perfectly. What happens when those cables actually break? Step 1. Let's read question 3. Consider 10 hosts named A to J connected in bus, one-way ring, star, tree, and full mesh topologies. Determine total links, hops, and how many hosts lose complete or partial connectivity when a single link fails.
Step 2, source tracing. This traces back to the specific mechanics on the network topology slides.
Step 3, exam strategy.
For the exam, do not try to do this in your head. Draw a quick physical sketch of the 10 nodes on the page. Mentally cut one wire with your pencil and count who can still talk to whom.
I like that. Okay, step 4, the deep dive. Let's run through them. I picture the bus topology like a single shared dinner table.
Okay, dinner table.
Yeah, if the table physically breaks in the middle, meaning the transmission medium fails, everyone suffers partial or full connectivity loss, you can't pass the salt to the other side of the room.
That's a great visual. Now compare that to a ring topology.
Right.
And the source specifically says a one-way ring. If you cut one link in a one-way game of telephone, the message stops dead. Every single host loses connectivity to the rest of the ring.
Oh, that is brutal.
Yeah.
Okay, what about the star topology? I love this one because it's like a 1920s telephone switchboard.
Right, with the central operator.
Yeah, all 10 hosts have their own wire running straight to the center. If host A's wire gets cut, only host A is isolated. That's a complete loss for one and 0 for the rest. They are totally fine.
True, but here is the twist you need to remember. Everything goes through the controller. If the switchboard operator fails, the entire network instantly goes dark.
Ah, right, the single point of failure. And finally, the full mesh.
Right. In a full match with 10 hosts, there are tons of links. 45, actually. So if one breaks, 0 hosts lose connectivity.
0.
0.
Right.
Because there is always another path. Host A just asks host C to pass the message to host B.
Ultimate resilience. Okay, so knowing the physical shape is only half the battle. We also need to know how we reserve the space on these wires to send a message. Step 1, question 4. This is an interactive exercise on circuit switching.
Step 2, source tracing. You'll find this on the circuit switching slides. It covers the 3 phases: establish, transfer, and disconnect.
So what's the step 3 exam strategy here?
The key exam trigger words for circuit switching are dedicated path, guaranteed performance, and no sharing. If you see those, it's circuit switching.
Step 4, let's dive in with an analogy. When I hear dedicated path, guaranteed performance, no sharing, I think of booking a high-end restaurant.
Okay, I see where you're going.
Yeah, circuit switching is like booking the entire restaurant for the whole night just for your family. Once established, the service is guaranteed. No one else is allowed in.
It sounds luxurious. But here is the critical why behind it. Circuit switching was designed for traditional telephone networks, voice calls.
Right.
But for data, it is highly inefficient. If your family eats for an hour and leaves the restaurant empty for the next 3 hours, that capacity is completely wasted.
Oh, I see, because no one else is allowed in the building.
Exactly. Holding an entire physical wire open just so you can read a web page for 10 minutes is a massive waste of space.
Which brings us to the modern internet. Since booking the whole restaurant wastes space, the internet uses packet switching instead. Let's do the hard math on how that works.
The math gets intense here.
It does. Step 1, question 5. Hosts A and B are connected via router R. Link AR is 10 MEPs and 2 kilometers. Link RB is 2 MEPs and 3 kilometers. Calculate transmission, propagation, and queuing delays for 1,500 byte packets. Find the first dropped packet in a 15,000 byte buffer and the average throughput.
Okay, step 2, source tracing. This points to the packet switching, store and forward slides, the packet delay, 4 sources slides, and the bottleneck link slides.
Got it. Step 3, exam strategy. What is the trick here?
This is the ultimate trap for students, unit conversions.
Oh.
The question gives you 1,500 bytes, but network speed is in bits. You must convert 1,500 bytes into 12,000 bits before using any formulas.
Oh, man. So if you miss that, the whole problem is wrong.
Entirely wrong. And another strategy tip, keep track of the packets chronologically on paper, like a train timetable, to calculate the queuing delay.
Okay, step 4, the PhD deep dive. We have transmission versus propagation delay. Let's use a physical analogy.
Go for it.
Let's say our 12,000-bit packet is a convoy of 12,000 cars.
Okay.
Transmission delay, which is length over rate, is just how long it takes that 12,000-car convoy to physically push out through a toll booth onto the highway.
Right.
But propagation delay, which is distance over speed, is the time it takes those cars to actually drive down the 2-kilometer highway at the speed of light.
That is brilliant. Pushing through the toll booth is transmission.
Yeah.
Driving down the road is propagation.
Exactly. But what about queuing delay and dropped packets?
Okay, so think of the router in the middle as a parking lot between 2 toll booths.
Right.
The first toll booth is pumping out cars at 10 millipics, but the second toll booth can only let them out at 2 millipics. It's 5 times slower.
Ah, so the cars are going to pile up in the parking lot. That's the queuing delay.
You got it. And that parking lot only holds 15,000 bytes. Once that lot is full, the very next packet that arrives literally falls off a crate. It's dropped entirely.
That is so chaotic, which explains why my internet lags when it's busy. Packets are just falling off a cliff.
Yep. And it leads to the final piece, throughput, the bottleneck link concept. The average throughput from A to B is strictly dictated by the slowest link.
So even though that first link is 10 MEPs?
The end-to-end throughput is choked down to exactly 2 MEPs.
Oh, well, congratulations. If you followed that, you just navigated from basic definitions all the way to calculating complex packet routing physics.
You really have gone from absolute beginner to exam-ready expert.
Yeah.
Just remember to trust the 4-step framework on your exam. Read the question, trace the source, find the strategy, and picture the real-world analogy.
Yes. And to leave you with one final kind of mind-bending thought based on this packet switching math, if packet switching treats every single packet independently,
Right.
and routers are basically these chaotic toll booths where data gets queued up, delayed, or just dropped entirely into the void when buffers overflow, how is it physically possible that we can have high-definition live video calls without it turning into a stuttering, out-of-order mess?
It's a great question.
Think about the sheer magic happening behind the screen to reassemble all of that chaos in real time. We'll let you mull that over. Catch you next time.